Today, we'll explore the foundational concepts of this intriguing the virtual number system, which extends the real numbers by introducing a new unit called j. This system is built around the virtual function, which we'll represent as v of k, and we'll use the notation v equals a times v of 0 plus b times v of 1 to describe virtual numbers. Let's dive in. The virtual unit j. The virtual number system introduces a new unit written as j, and it is defined by the equation j equals the natural logarithm of -1. This means j is not a real number. In other words, j does not belong to the set of real numbers. This is similar to how the imaginary unit, typically written as I, extends the real numbers in the complex number system. However, j has its own distinct properties, which we'll explore in this series. A virtual number is expressed as v equals a times v of 0 plus b times v of 1. Here, a and b are real numbers, and the virtual functions v of 0 and v of 1 are defined as follows. V of 0 equals 1, which acts as the multiplicative identity. V of 1 equals j, which is the virtual unit we just introduced. So rewriting a virtual number using these definitions, we get v equals a times 1 plus b times j, which simplifies to a plus b times j. This notation is similar to how complex numbers are written, but remember, j is not the square root of -1. Axioms of the virtual number system. Let's go through the fundamental axioms that define the virtual number system. These axioms establish the structure and rules for operations. Axiom 1. Existence of the virtual unit j. There exists a virtual unit j such that j equals the natural logarithm of -1. As we mentioned before, j is not a real number. This distinguishes it from numbers we typically use and gives virtual numbers unique properties. Axiom 2. Form of virtual numbers. Every virtual number can be written in the form v equals a times v of 0 plus b times v of 1, where a and b are real numbers. The set of all such virtual numbers is called V, the virtual number system. Axiom 3. Equality of virtual numbers. Two virtual numbers are considered equal if and only if their coefficients match. In other words, if v1 equals a 1 times v of 0 plus b1 times v of 1 and v2 equals a 2 times v of 0 plus b2 times v of 1, then v1 equals v2 if and only if a1 equals a2 and b1 equals b2. Axiom 4. Addition of virtual numbers. For two virtual numbers, v1 equals a1 times v of 0 plus b1 times v of 1 and v2 equals a2 times v of 0 plus b2 times v of 1, their sum is given by v1 plus v2 equals a1 plus a2 times v of 0 plus b1 plus b2 times v of 1. This means that addition in the virtual number system follows the same rules as addition in real numbers. It is both commutative and associative. Axiom 5. Scalar multiplication. For a real number c and a virtual number, v equals a times v of 0 plus b times v of 1, the scalar multiplication is given by c times v equals c times a times v of 0 plus c times b times v of 1. This means that when multiplying a virtual number by a real number, each coefficient is multiplied individually. Example calculations. Let's work through an example. Consider two virtual numbers. v1 equals 2 times v of 0 plus 3 times v of 1. v2 equals 4 times v of 0 plus 5 times v of 1. Using the axioms, we can compute their sum. v1 plus v2 equals 2 plus 4 times v of 0 plus 3 plus 5 times v of 1. This simplifies to 6 times v of 0 plus 8 times v of 1. Similarly, if we multiply v1 by a scalar c equals 2, we get 2 times v of 0 plus 3 times v of 1 equals 2 times v of 0 plus 2 times 3 times v of 1. This simplifies to 4 times v of 0 plus 6 times v of 1. In this chapter, we'll dive deeper into the concept of the virtual function, denoted as v of k. This function is at the heart of the virtual number system, and in this video, we'll explore its recursive definition, its properties, and how it allows us to define higher-order virtual numbers. Let's get started. Recursive definition of v of k. The virtual function v of k is defined recursively using the following rule. V of k equals the natural logarithm of -1 raised to the power of v of k minus 1. The Shah base case is v of 0 equals 1. This means that each value of v depends on the previous term. Let's break this down. The base case, v of 0 equals 1, is known as the multiplicative identity in this system. That means if you multiply any virtual number by v of 0, it remains unchanged. For example, if we take a general virtual number written as v equals a times v of 0 plus b times v of 1, this simplifies to a times 1 plus b times j, which is just a plus bj. Now let's compute v of 1. Using the recursive definition, v of 1 equals the natural logarithm of negative 1 raised to the power of v of 0. Since v of 0 equals 1, this simplifies to the natural logarithm of negative 1 raised to the power of 1, which is simply j. So we have v of 1 equals j, which is the same virtual unit we introduced earlier. Next, let's compute v of 2. Again, using the recursive definition, v of 2 equals the natural logarithm of negative 1 raised to the power of v of 1. Since v of 1 is j, this simplifies to the natural logarithm of negative 1 raised to the power of j. This is a higher-order virtual number, and its exact value depends on the properties of j. For now, we'll treat v of 2 as a new element in the system. Properties of the virtual function. The virtual function v of k has some interesting properties that help us simplify calculations. Let's go through them. The behavior of a number times v of k depends on whether the number is even, odd, or something else. Here are the rules. 1. If the number is even, then multiplying it by v of k gives 0. 2. If the number is odd, then multiplying it by v of k gives back v of k. 3. If the number is neither even nor odd, such as a fraction or an irrational number, then it simply remains as it is. Let's apply these rules with some examples. First, let's take 2 times v of 1. Since 2 is even, the rule tells us that this must be 0. Now let's take 3 times v of 1. Since 3 is odd, the rule tells us that this is just v of 1. These rules allow us to simplify expressions involving v of k quickly and efficiently, higher-order virtual numbers. Now let's explore even higher-order virtual numbers. From the recursive definition, we found that v of 2 equals the natural logarithm of negative 1 raised to the power of j. Following the same pattern, we compute v of 3. v of 3 equals the natural logarithm of negative 1 raised to the power of v of 2. Since v of 2 is already an exponential expression, this results in a nested exponentiation involving the natural logarithm of negative 1. At this stage, these higher-order virtual numbers take on unique properties depending on how we define the behavior of j. For now, we'll treat them as new elements in the system and continue to explore their implications in future discussions. In this chapter, where we'll explore exponentiation in the virtual number system. Specifically, we'll examine how the exponential function behaves when applied to virtual numbers and how it connects to the virtual function v of k. Let's dive in. Exponentiation in the virtual number system. In this system, the exponential function of a virtual number v of k is defined as e raised to the power of v of k equals negative 1, raised to the power of v of k minus 1. This definition creates a recursive connection between exponentiation and the virtual function. Let's break this down step by step. Base case, exponentiation of v of 0. First, let's consider the base case where v of 0 equals 1. Using our definition, we get e raised to the power of v of 0 equals negative 1, raised to the power of v of negative 1. However, v of negative 1 is not defined in our system, so we'll only focus on cases where k is greater than or equal to 1. For k equals 1, we compute e raised to the power of v of 1 equals negative 1, raised to the power of v of 0. Since v of 0 equals 1, this simplifies to negative 1 raised to the power of 1, which is just negative 1. So we conclude that e raised to the power of v of 1 equals negative 1. Exponentiation of higher-order virtual numbers. Next, let's compute e raised to the power of v of 2. Using the recursive definition, e raised to the power of v of 2 equals negative 1 raised to the power of v of 1. Since v of 1 equals j, this simplifies to negative 1 raised to the power of j. At this point, we encounter a higher-order virtual number. The exact value of negative 1 raised to the power of j depends on the properties of j. For now, we'll treat this as a new element in the system. Relationship between exponentiation and the virtual function. There is a deep connection between the virtual function v of k and the exponential function. Recall the definitions. v of k is equal to the natural logarithm of negative 1 raised to the power of v of k minus 1. On the other hand, e raised to the power of v of k is equal to negative 1 raised to the power of v of k minus 1. This suggests that exponentiation and the virtual function are related in an inverse way. Let's explore this further. From our earlier results, we found that e raised to the power of v of 1 equals -1, while v of 1 equals j. This shows that e raised to the power of j equals -1. Interestingly, this resembles Euler's formula, where e raised to the power of I times pi equals -1 in the complex number system. However, in our system, j is defined as the natural logarithm of -1, which leads to a slightly different relationship. Higher-order exponential expressions. Now let's analyze the behavior of exponentiation for higher values of k. For k equals 2, we already found that e raised to the power of v of 2 equals -1 raised to the power of j. For k equals 3, we extend this pattern. E raised to the power of v of 3 equals -1 raised to the power of v of 2. Since v of 2 itself is an exponentiation involving j, these expressions become nested exponentials of -1. Their exact values depend on how j and v of 2 behave. For now, we'll consider them as new elements in the system to be explored further in later discussions. This chapter, where we'll explore multiplication in the virtual number system. We'll define the product of two virtual numbers and examine how higher-order terms like j squared and j cubed behave. Let's dive in. Multiplication of virtual numbers. Let's start by defining the product of two virtual numbers. Suppose we have v1 equals a1 times v of 0 plus b1 times v of 1, and v2 equals a2 times v of 0 plus b2 times v of 1. Their product, v1 times v2, is defined as v1 times v2 equals the quantity a1 times v of 0 plus b1 times v of 1, multiplied by the quantity a2 times v of 0 plus b2 times v of 1. Let's expand this step by step. Using the distributive property, we can rewrite the expression as v1 times v2 equals a1 times a2 times v of 0 squared plus a1 times b2 times v of 0 times v of 1 plus a2 times b1 times v of 1 times v of 0 plus b1 times b2 times v of 1 squared. Now let's simplify each term using the properties of v of 0 and v of 1. First, recall that v of 0 equals 1. Therefore, v of 0 squared equals v of 0, which equals 1, and v of 0 times v of 1 equals v of 1. Similarly, v of 1 times v of 0 equals v of 1. Using these properties, we simplify the product to v1 times v2 equals a1 times a2 times v of 0 plus the quantity a1 times b2 plus a2 times b1, all times v of 1 plus b1 times b2 times v of 1 squared. Simplifying higher-order terms. Now let's simplify v of 1 squared. Recall that v of 1 equals j, so v of 1 squared equals j squared. From the recursive definition of the virtual function, we have v of 2 equals the natural logarithm of -1 raised to the power of j. So we conclude that v of 1 squared equals v of 2. Thus our final expression for the product of v1 and v2 becomes v1 times v2 equals a1 times a2 times v of 0 plus the quantity a1 times b2 plus a2 times b1, all times v of 1 plus b1 times b2 times v of 2. Example. Let's work through an example. Consider v1 equals 2 times v of 0 plus 3 times v of 1, and v2 equals 4 times v of 0 plus 5 times v of 1. Their product is calculated as follows. v1 times v2 equals 2 times 4 times v of 0 plus the sum of 2 times 5 and 3 times 4, all times v of 1 plus 3 times 5 times v of 2. Simplifying the coefficients. v1 times v2 equals 8 times v of 0 plus the sum of 10 and 12 times v of 1 plus 15 times v of 2. This simplifies further to v1 times v2 equals 8 times v of 0 plus 22 times v of 1 plus 15 times v of 2. Behavior of higher-order terms. Now, let's discuss the behavior of higher-order terms like v of 2 and v of 3. Recall that v of 2 equals the natural logarithm of -1 raised to the power of j, and v of 3 equals the natural logarithm of -1 raised to the power of v of 2. These terms involve nested exponentiation of the natural logarithm of -1. Their exact values depend on the properties of j. For now, we will treat them as new elements in the system. In this chapter, we're diving into two really important properties of the virtual number system. These properties are associativity and closure. Specifically, we'll prove that multiplication is associative and that the system is closed under addition and multiplication. So grab your favorite notebook and let's get started. Alright, first up, associativity. What does it mean for multiplication to be associative? It means that no matter how you group three numbers when multiplying them, the result will always be the same. For example, if you have three virtual numbers, let's call them v1, v2, and v3, the following equation should hold true. The product of v1 and v2 multiplied by v3 equals v1 multiplied by the product of v2 and v3. Now let's break this down step by step. To start, let's define what these virtual numbers look like. Each virtual number can be written as a combination of two components, one part involving v of 0 and another involving v of 1. Specifically, we'll say v1 equals a1 times v of 0 plus b1 times v of 1, v2 equals a2 times v of 0 plus b2 times v of 1, and v3 equals a3 times v of 0 plus b3 times v of 1. Here a1, b1, a2, b2, a3, and b3 are just real numbers. Now, our goal is to compute both the product of v1 and v2, then multiply that by v3, and v1 multiplied by the product of v2 and v3, and show that they give the same result. First, let's compute the product of v1 and v2. From earlier work, we know that v1 times v2 equals a1 times a2 times v of 0, plus a1 times b2 plus a2 times b1 times v of 1, plus b1 times b2 times v of 2. Got that? Great. Now, let's take this result and multiply it by v3. Okay, so now we're computing the product of v1 and v2, then multiplying that by v3. Let's expand this step by step. When we multiply everything out, we get a1 times a2 times a3 times v of 0, plus a1 times a2 times b3, plus a1 times b2 times a3, plus a2 times b1 times a3 times v of 1. Plus a1 times b2 times b3, plus a2 times b1 times b3, plus b1 times b2 times 3 times v of 2, plus b1 times b2 times b3 times v of 3. That's quite a mouthful, but don't worry, we'll compare this with the other grouping soon. Now let's switch gears and compute the product of v2 and v3. This gives us a2 times a3 times v of 0, plus a2 times b3, plus a3 times b2 times v of 1. Plus b2 times b3 times v of 2. Next, we'll take this result and multiply it by v1. When we compute v1 times the product of v2 and v3, we get a1 times a2 times a3 times v of 0, plus a1 times a2 times b3, plus a1 times a3 times b2, plus b1 times a2 times a3 times v of 1. Plus a1 times b2 2 times b3, plus b1 times a2 times b3, plus b1 times a times b2 times v of 2, plus b1 times b2 times b3 times v of 3. Notice anything familiar? Yep, this looks almost identical to what we got earlier. Now let's compare the two expressions. On one side we have the product of v1 and v2, then multiplied by v3. On the other side we have v1 multiplied by the product of v2 and v3. And guess what? They're exactly the same. Both expressions simplify to a1 times a2 times a3 times v of 0, plus a1 times a2 times b3 plus a1 times b2 times a3 plus a2 times b1 times a3 times v of 1, plus a1 times b2 times b3 plus a2 times b1 times b3 plus b1 times b2 times a3 times v of 2, plus b1 times b2 times b3 times v of 3. Since the two results match, we've proven that multiplication is associative in the virtual number system. All right, now let's move on to the second property, closure. A system is said to be closed under an operation if applying that operation to any two elements in the system always produces another element in the same system. We'll check this for both addition and multiplication. First, let's look at addition. From earlier videos, we know that adding two virtual numbers works like this. v1 plus v2 equals a1 plus a2 times v of 0 plus b1 plus b2 times v of 1. Since a1 plus a2 and b1 plus b2 are just real numbers, the result is still a valid virtual number. Therefore, the system is closed under addition. Next, let's check multiplication. Again, from earlier work, we know that v1 times v2 equals a1 times a2 times v of 0 plus a1 times b2 plus a2 times b1 times v of 1. Plus b1 times b2 times v of 2. Here a 1 times a2, a 1 times b2 plus a2 times b1, and b1 times b2 are all real numbers. Since v of 0, v of 1, and v of 2 are part of the system, the result is still a valid virtual number. Therefore, the system is also closed under multiplication. And there you have it. We've proven that multiplication is associative and that the virtual number system is closed under both addition and multiplication. These properties make the system consistent and reliable for further mathematical exploration. In this chapter, we're diving into two important concepts in the virtual number system: the conjugate and the multiplicative inverse of a virtual number. These ideas are crucial for understanding the algebraic structure of the system. So grab your favorite notebook and let's get started. First, let's define what we mean by the conjugate of a virtual number. For any virtual number written as a times v of 0 plus b times v of 1, its conjugate is defined as a times v of 0 minus b times v of 1. This is very similar to how we define the conjugate of a complex number. For example, if you have a complex number z equals a plus bi, its conjugate is a minus bi. The same idea applies here, just flip the sign of the coefficient of v of 1. To make this clearer, let's work through an example. Consider the virtual number v equals 2 times v of 0 plus 3 times v of 1. Its conjugate would be 2 times v of 0 minus 3 times v of 1. So the conjugate simply changes the sign of the coefficient of v of 1. Easy, right? Next, let's move on to the multiplicative inverse of a virtual number. The inverse of a virtual number v is defined as the conjugate of v divided by the product of v and its conjugate. In mathematical terms, that's v inverse equals the conjugate of v divided by v times the conjugate of v. Let's break this down step by step. First, we need to compute the product of v and its conjugate. Let's say v equals a times v of 0 plus b times v of 1, and its conjugate is a times v of 0 minus b times v of 1. When we multiply these two together, we get a squared times v of 0 squared minus a times b times v of 0 times v of 1 plus a times b times v of 1 times v of 0 minus b squared times v of 1 squared. Now, let's simplify this expression. We know from earlier rules that v of 0 squared equals v of 0, and v of 0 times v of 1 equals v of 1. Using these simplifications, the expression becomes a squared times v of 0 minus b squared times v of 1 squared. Finally, recall that v of 1 squared equals v of 2. So we can rewrite this as a squared times v of 0 minus b squared times v of 2. Now, since v of 0 equals 1, we can simplify this even further. A squared minus b squared times v of 2. This result isn't a real number because of the v of 2 term, but it's still a valid element of the virtual number system. With this result in hand, the multiplicative inverse of v becomes v inverse equals the conjugate of v divided by a squared minus b squared times v of 2. Substituting the conjugate of v, which is a times v of 0 minus b times v of 1, we get v inverse equals a times v of 0 minus b times v of 1, all divided by a squared minus b squared times v of 2. This expression gives us the inverse of v, but it still depends on v of 2. To fully simplify, we'd need more information about how v of 2 behaves. Let's look at some special cases to make this clearer. First, consider the case where b equals 0. If b equals 0, then v equals a times v of 0, which is just a real number. In this case, the inverse is straightforward. V inverse equals 1 over a times v of 0. This is the standard inverse of a real number. Next, consider the case where a equals 0. If a equals 0, then v equals b times v of 1. Its inverse becomes v inverse equals negative b times v of 1 divided by negative b squared times v of 2. Simplifying this, we get v inverse equals v of 1 divided by b times v of 2. This expression still depends on v of 2, so without additional rules, we can't simplify it further. And there you have it. We've explored the conjugate and multiplicative inverse of a virtual number, breaking them down step by step. These concepts are foundational for understanding the algebraic structure of the virtual number system. If you found this video helpful, don't forget to like, subscribe, and hit that notification bell so you never miss an update. Got questions or topics you'd like us to cover? Drop them in the comments below. Thanks for watching, and I'll see you in the next one.